Okay, so now we come to the first part of the main tools for performance evaluation, right, and that is our Markov processes, Markov chains. We have heard those terms, right. So what is a Markov process from what you know? What is a Markov from your definition, from what you remember, and what is it used for? Nobody wants to make a guess.
System can be in a number of states at every instant point in time. So, and given that it is in a state, currently there is a probability that it goes to the next state.
Yes. Okay. So, yeah. So this is to capture the state of a system. Usually, right? We want to model a system. That is ultimately where, right? Performance modeling is what we are trying to do. So we want to model the behavior or operation of a given system, and we define certain values or parameters to capture the state of a system. These are usually state variables. Parameters is not the right word. State variables, right? That capture the current state of a system. And then we want to represent that. We all talk about state transition diagrams, right? State transition diagrams we know about. We use that to represent behavior, but that is usually only to represent functional, like a flow chart, right? So what happens if, or event, so if you are in state 1 and depending on whichever event occurs you go to some other state and so on. So that is simply to depict the operation, the behavior of the system itself. But Markov chains are very similar, or Markov processes in general are similar. In general, stochastic processes try to capture the state of a system as with some variables, and it models the behavior through a state transition. So you are right now in state X, then what is the probability you will go to state Y, right, in some time. How long will you stay in the state X, and when will you go to state Y, and what is the probability of going to some other neighboring state, and whether you can go from only one state to neighboring state or one state to some other state and so on. So all those things come under this class of stochastic processes. So Markov processes are useful many times, they come in handy, and some systems are amenable to it, some systems are not amenable to it. We will look at some systems where we can actually use it very effectively. So the first example we look at is in the context of queuing systems, right. So queuing systems, we can very easily derive several closed form solutions with the help of these Markov chains and Markov processes and so on, right. So before I get into that, I just wanted to give some background definition for many of these terms, right. Even I was a little bit loosely using, as I said, processes, variables, right. So now let us try to say, so random variable is what we have seen now, right. So a random process or stochastic process is where I have repetitions, right, where each of those let us say each of those repetitions will have this some kind of distribution, right. So if I say the same thing, Bernoulli, right. So Bernoulli trial, right, I just flip a coin, that is one trial, then I keep repeating that trial, then that ends up as a Bernoulli process, and then the probability of getting a heads or tails on each of those trials within this process, right, could stay stationary or it could be not stationary, right, because if we keep tossing a coin, it is possible that the coin could become unfair for whatever reason, it keeps falling on ground, therefore dead sticks on one side of the coin, therefore ends up falling on that particular coin, right. Therefore it need not be stationary. So even if I take a coin and keep tossing it, over time the probability of heads and tails might change, right, it's a loaded dice or just this way, right. So that's where we will look at a random variable, which is experiment conducted across time. So a series of random variables over some parameter, which we normally is time, will be our so called stochastic process, and within that some very specific cases are there, which is what we can easily use for analysis, right. So that's just go through some of those definitions initially, otherwise I can simply say here is a Markov process, but let us just know what how we get the Markov process through a series of these special cases, okay. So we are going to look at stochastic processes, and this again is not in detail in the Raj Jain book. Raj Jain straight away goes into Markov chain, right, but this I am using from our KST. Is a Kishore Trivedi's book, right. So this book I have here is the older 82 edition. So a stochastic process. So some little bit of definitions again will be there. Now there will be more wordier definitions because not everything is an equation, right. So lots of words to write, which is easier to do on the board, but anyway let us try to do it here too. Okay, so a stochastic process is basically a family of random variables. indexed by some parameter. Okay. So from variable we progress to process. So series of this variables indexed by some time. So for example, a student, IIT student or elsewhere, right, who never prepares for any exam and simply, right, flips or prepares, but he flips on a random basis, right, he flips through some pages and hopes that those questions will appear, and then he writes all his exams that way. And then you look at the GPA every semester, right. So GPA is a random variable at that point because there is random preparation. And then we look at all the 8th semester GPA, that becomes a stochastic process, right, because your index is now that parameter is your semester, right. So every semester you have a different value which is based, maybe the same distribution is used, right. If you randomly flip, maybe you will end up with the same distribution of grades, but somehow, right, that is let us not worry about that. So that is your example of a random process. So the series of GPAs where each GPA, each grade, right, is a random variable. That is an example of what a stochastic process would be, right. So we normally use this notation x of t. X is the random variable and t is my, and t need not be time, t can be any discrete set, okay, but normally we look at what happens over time with respect to this.
So in your example, suppose there are 6 students in one semester.
Okay.
All 6 are studying randomly they open subjects. So everybody's GPA will become one random variable.
As we have 6 stochastic processes.
So the 6 stochastic or total 6 random variables will make it one stochastic process.
But see, I have to define in each, for each instant of time, right, I have to capture the state. So if you are
independent of time, I'm just taking these 6 random variables.
Okay, so you are saying
it as semester wise, I'm taking only in one semester.
Oh, okay, so you are indexing by the students.
Yes.
Right, so you have 6 students and or maybe, okay, so then here there is okay, see what happens is usually you need with time some changes, okay. See here there is no notion of time, right, your discrete parameter is
6 separate processes, or it is only one process with 6 variables.
Okay, see with the stochastic process we need to, right, move from one state to another. So in this case, how do we describe the moving from one student to another student is technically unrelated, right. So the GPAs of the students are unrelated or sort of completely or different random variables. So I would not call that as a family, even though the student, yeah. So I would rather look at this as a one student over time, right, what is happening.
If we take all 4 semesters and thereafter do it, then can we say that there will be 6 variables in this process and each variable will be moving like on 4 instances?
As a moving average of 4 semesters. Yes. You are talking about moving average. That's also random. So then if you look at only every semester you are computing, but after the 5th semester or after the 4th semester, then that is also fine, right. But what happens is there is some dependence there, right, because now you are, in this case these all semester grades are independent, but there will be some dependency, that is fine. Then that is where we come and define our Markov where there is no dependence, right, on all the previous states. Only for example, if my grade in my 5th semester only depends upon my performance in the 4th semester, does not depend upon my performance in the other semester, which is used for prediction, right. It is the other way around. If I want to predict whether I want to take the student as a project associate or not, or as a MTech or BTech student, then I usually use the grades as a predictor, right. So if you look at the 4 or 5 semesters and then say the 6th semester grade will most likely depend upon these previous 5, but that is we are entering a different space of prediction and so on. That is something that Hema madam tries to do.
Coming back to your example, one student is different GPA for each semester. How are you relating them together? How are they dependent on each other?
he is just studying randomly,
Yeah.
typing some pages, he is getting some GPA which is also random. They may
Yes.
be same, they may not be same.
Yeah.
So how are they dependent on each other?
But time is where I am trying to, so I am looking at this as a time progression, right, as a series of time based events. So I am looking at one student here. Yeah, here there is yeah, so that is why I am saying this, each semester the student is preparing totally randomly, so therefore there is no memory. I can also define a system where there is dependence as you progress from one state to another, right. So initially you could be a 7.5 GPA student, then you learned from mistakes, then you became 8.1, you still learned better, so you could progress that way also. That is also a stochastic process, that is fine. I am just giving that as a case where there is complete independence, but you can have dependence between the states too, right. So to go from 7 point, let us say that I am looking at only 6 discrete states, right, A through F, these are the only possible states, there is no F here, right. So but fine, A through F, and each semester I give you you get classified as either A or F and so on, right. So you start off in your first semester as a say B student, right, that is what we normally say, right. We have our 7 point someone, right, so you are 7 point student, right. Then the next semester we look at your GPA, and then your GPA will be of course including your old grades also, but maybe whatever you learned from the previous semester you become, right, some other class student and so on. So there is some sort of time progression there, and where Markov comes in we will see later on is where the state that you are in currently, right. So after 4 semesters you are in a particular state, that state probability distribution for that state, whether you are A, either probability A is 10%, B is 20%, so on, that depends upon either your previous state or none of the states at all, right. If they are completely independent it can be 2, right, each of the states can be totally independent of each other, or there is some dependence on your past states. All of this will come under your general classification of a stochastic process, right. Come in, yeah. So this x of t, right, so this x of t that I am showing here, this is a distribution. Your distribution can be stationary with respect to time or it can vary with respect to time, right. So for example at let us say we just use this example, right, you are only 3 classes, right. So probability of getting an A, right, is 30%, probability of getting a B is 30%, C is 40%. This is some distribution initially when you start off in the system, right. Then after maybe time instant 1, right, something has happened, whatever, there is things have gone on, then let us say this could be the same as that or it could be changed over also. Okay, this is also fine, right. So this is, so for every event of time, every instant of time you have a distribution for this random variable x, right, that can be stationary, time stationary or time varying. So now
same random variable, different time instance.
Yeah, same. Yeah, different at different time instances. The distribution for this random variable. See, I am collecting these x's together as one stochastic as a process, right? Yeah. So my family is x0, x1, x2, and so on. So at every instant of time there is one random variable. Yeah. So that's this collection of random variables is my stochastic. Okay, so let us look at this non-GPA example, right. So let us look at packet arrival process, right. So in the arrival process what I measure is the inter-arrival time. What is the time between 2 successive arrivals? That is the random variable, right. So at the beginning of the system I am saying that packets will arrive by exponential process, right, with some distribution, and if it is completely stationary, right, and I say that the inter-arrival time is exponentially distributed with mean say 1 packet per second or with mean of 1 second, right, that is my definition of that exponential variable. So between every successive, right, see this is the first arrival, right, this is a random variable that I would say call x of 1, this has some distribution, right, this is some distribution, I am saying that this is a e power, right, minus lambda x, some parameter a is there. Then I look at the next time to the next arrival, what is that? That is also a random variable, it could be following the same distribution, right, or it could depend upon the fact that the packet has arrived, okay. This is another random variable technically, right, and so on. So the different inter-arrival times, the sequence of inter-arrival times forms your forms this family of random variables, right. So if this is a Poisson process, right, then the interarrival times are exponential, and then the parameter does not change, right, your lambda does not change with respect to, here your indexing is based on the packet number, the index is not the time, right, index is now simply the packet number 1 2 3 4 and so on, so discrete state or discrete parameter which is indexing it, right. So it is not necessarily time, but in this case it is the, I am looking at what is the time between successive arrivals, right. So this forms your stochastic process. And or again another example is, this is arrivals, right, this is inter-arrival time. Or if you look at a machine, right, then the lifetime, the machine will have faults and get fixed, and it runs again it gets fault, so the mean time to failure, right, that is also a random variable. So the classic case which we know is that, between different arrivals, that this parameter a does not change, that is a looks pretty bad. If the parameter a does not change between the different variables, then that is we will look at it formally as a time stationary process.
This package can arrive from any number of sources.
Yes, yeah. So I am just looking at, for a queue, packets are arrive from one source, multiple sources, and so on. Okay. Any other questions? I've been answering. Okay, so we'll have to stop here. So the values assumed by this x of t, we will call them states from now on. Called the state space. So there are two things, one is the set of states that are possible, right, and the other is the set of parameter values, that parameter t, right, the t is the set that I talked about, the parameter set. So based on that we will have some 3 or 4 classifications, right. So the state space can be discrete or continuous, right. So state space, for example, if you are measuring the number of customers in a system, right, that you count every 10 seconds or so, that becomes that's a fine, that's a discrete number, right. Whereas if you are measuring the service requirement at a given point in time, you look at all the customers waiting in the system and you take the sum of the service times of all the customers, that is also a state space, right, that is a thing that represents the state, for whatever reason you want to measure that is a continuous variable, right. So the state space can be either discrete or continuous, and likewise your parameter t, right, this is a parameter can be discrete or continuous. So discrete time would be just looking at specific instance of time, integral values of time, right, 1 2 3 4, or only looking at arrivals. If you only look at the system when the first arrival comes, second arrival comes, third arrival comes and so on, right, then you have a discrete parameter space. But if you are looking at t as general time and you do not care, right, any point in time I want to measure the average number of customers in the system or the average service time, total wait service time for all the customers in the system, then it becomes, then your parameter space becomes continuous, right. So your parameter space can be discovered. This gives rise to 4 different systems, right. You have a discrete parameter, continuous state, discrete parameter, discrete state, and so on. So we have 4 combinations, and we will take a look at what those combinations are. So you have discrete state, so we have discrete, usually we, whenever it is parameter we simply usually refer to it as time, discrete time, discrete state, discrete time, continuous state, continuous time, discrete state, continuous time, continuous state, 4 possible systems. This is important because when you look at a system, each of these has different properties, right. So now we need to come up with some examples of each of these, right, so that we understand what each of these we are talking about. So let us look at a queue. So we are now beginning to start thinking about queue. So this is my representation of a queue. There is a buffer, there is a server, customers enter and customers leave the system, right. So in this system, if I define a variable where we measure the number of customers in the system or number of packets in that buffer, whatever it is, say, so my variable is basically, right, nk, we will call that, k is 1, 2, 3. So what is this? What type of variable is this, or stochastic processes? So this is your DTDS, right? Okay. Then you measure the waiting time, right, of the kth customer. So you look at every customer and measure its waiting time before it gets service. So the amount of time spent in the queue, right, that is what this Wk is, right. So k will be again 1 to infinity, right. So this is discrete time, continuous state, because your state is now any value, right, or any non-integer value. So can you think of a continuous parameter discrete state?
So why you took it as continuous state?
because waiting time is, it's not integral, it's not an integer, waiting time in the queue, right, because that depends on the service times can take your exponential distribution, so they need not be integers, right. The number of customers in the queue at any point in time, that is your example of a continuous time discrete state, right. So we will say represent this by say E and T. We looked at in queuing theory in our networks class, we saw this, right. So we actually computed E of n, we only looked at the expected value, but you can also look at the distribution, right. So T would be T is positive, so any value of T greater than to infinity. So that is your continuous, right. So this is an example of continuous time discrete state. Then for continuous time continuous state, yeah, total waiting time, total service time, right, something that is. So if I use say at y of t is a cumulative So let us revisit our stochastic processes. Okay. So from random variables we went to a collection of random variables or family of random variables, right, that is what this one represents. So from this I want to go to Markov. I might skip some definitions along the way. Okay. So essentially what we have is, right, if you look at some parameter which we call as t, right. So there is a random variable, right. So whatever is the state of the system is captured by x of this is time t1, right. So x of t1 is the state of the system at time t1, and that is described by some random variable xt1, right. So and then at time t2 you have another, right, xt2. So these are essentially potentially different random variables, right. They may be dependent, they may be independent, but that is all the different classifications, right. If they are independent, then it forms a renewal process and things like that, right. So all we have is now a series of these random variables that is capturing the state of the system and the evolution of the state of the system with respect to some discrete some parameter t, could be discrete or continuous. Yes, we have multiple variables also. So mostly we look at single just as a state as a sequence of 0, 1, 2 and so on, but that is supposed to somehow encode what are the different values that you have. Right. Later on we will see if we go to 2D Markov chain when we look at sequence of queues in tandem.
Can you give some physical example in network how what you state of
Okay.
in network, suppose a queue is there, so you are taking the random variable process arrive till that time.
Yeah, so we saw this queue the other day, right. We saw a set of examples, set of variables. So for example the number of customers in the system at the kth departure, right, that is the state of the system. So nk, you look at the state of the system at those discrete instants when customers are leaving the system, right. When a given there is only one server, customer is finishing service and is leaving the system, at that time you look back and see how many people are still in the system, right, that is your nk. So that is an example of the state of the system, and then what we would use that as a model to find out how many average customers are there in the system, and then from that we derive what we derived last time, right, delay throughput and things like that. Or it could be simply at every time instant, right, simply that is only when a customer k is leaving, or at all times t, right. So as a continuous time on a continuous time scale, look at the number of customers in the system. So it is like almost monitoring, right, every nanosecond or so, and look at how many customers are there, how many customers are there, and then use that to represent the state of the system. Or look at it every 1 second and say at every 1 second interval you measure the state of the system, where the state of the system in this case is the number of customers in the system including those in service. So whatever we define as a state, if we look at the transition of the state, right, over time with respect to this time or some other metric that is used to characterize. Okay. Okay. So just a couple of definitions, then I will get straight into Markov. Right, some of these things are kind of too much of a distraction. So at right, so time t equals t1. Right, so we can look at the CDF of this random variable, right. You can represent that by, so just want to get to the fact that the system state is captured over a series of time instants, right, t1, t2 and so on. So this is a simple, right, so if it is x1,
So this interval which we are taking, whether it is time or something, has to be continuous
no, it need not be.
or uniform.
No, it need not be. That is why we looked at continuous time, discrete time and so on, right. So for example, in the case of customer leaving a system, there those are specific time instants. I am only interested in the departure of the k is, for example, first customer, k goes from the index, right, that parameter set t is discrete, k 1, 2, 3 and so on, because there I am only looking at when the kth customer is leaving the system, right. So we do not care what time it is, only caring about what is the k, right, and for k is simply an integer that is indexing the different customers leaving. Or if you look at time, then it is, even the other example you look continuous time, looking at the average waiting service or the number of customers in the system at every instant of time, then that is there your time is continuous, right. So that is why we have this combinations of discrete time, continuous time, right. So this is our standard, right, this is a default definition, right, at t1 that what is the CDF of x of t1, right. So this is called the first order, right. So now let us say that the system is progressed, right, to some time t2. So the above was first order, so to describe a stochastic process, right, I have to what happens in the next time instant and third time instant and so on. So it gets to be fairly complex if I want to exactly capture the behavior of a system. So second order distribution is given by, so x1 x2 two variables, t1 t2, right. So this is the CDF of of this x1 and x2 combined together. So that is so what is a CDF, or what is the probability that the system will have less than or equal to, the state of the system will be less than or equal to x1 at time t1 and x2 at time t2, that is the second order distribution of the system itself. So ideally we should have some description of this, which is not possible in all cases, but this is what is describing the system behavior as time evolves, right. So I need, so the system is defined by this distribution, the CDF function that we are defining, right. Make sense. So if it is a discrete variable, we will have a set of PMFs that says what is, let us say there are two possible. So if x1, right, is 0 and 1, right, and x2 is also 0 and 1, then I will have a joint PMF that describes what is the probability that x1 is, right, at time t1, right. So if you look at t1 t2, at time t1 what is the probability the system was in state 0, and at time t2 what is the probability the system was in time, right, in state 0, or 0 1 1 1 0 1 1. So this would be my cumulative, this CDF, right. So in this case I will describe it as a mass function. I will say that the probability, right, system being this could be whatever that we think of, so 0.25 and say 0.35. That you can figure it out, 0.2, right. So this is the characterization of the system behavior. Now how do we get to this? This depends upon understanding, right, what is the probability of going from one state to another state, right. So for example, if the channel being transmitted initially maybe in a good state, right. So let us say you start off with being a channel in a good state, then you measure the channel at some other time in the future and you find the channel has entered noisy state and therefore the next state is noisy. So 0 is good state, 1 is noisy state. So what is the probability of being in a good state before and a good state now, and likewise, right. So this is determined by the channel characteristics, right, as to what is the level of noise in the system, what is the kind of modulation scheme and so on. So all those P's will enable us to calculate such a table. Which one? This is AND. This is AND. What is, it's not conditional. This is simply AND. In conditional we will see, right. This is simply describing the behavior of the system where what is the probability for each of these combinations happening, that is all, right. So then I can extend this further to the so called nth order, where I will use this vector x to denote all the possible x values and t to denote my time values. So this is this massive, right, what is the probability that x of t1 is this. So if I can come up with a distribution like this, either analytically or simply measured, that is what describes the state of the system. With this we will have to do some other manipulations. If I know this, I can do some other operations on the system to get to some, right. So this is what is called the nth order distribution of the system as it is evolving with respect to this discrete time instance. So what you will find is that as the system evolves over a long term, right, then this might converge to some stationary probability distribution, right, some stationary distribution where regardless of whether it is 1000th interval or 1001st interval, the probability of all these the CDF of these individual of this combined set of variables is going to be stationary, does not change with respect to time. Initially it might be changing, but over a long period of time it may simply be stationary. So that I am not defining specifically, but it is there in the book. Just assume that in the long run, right, this distribution becomes stable. Okay, where will this be used? This will be useful for computing your stationary probabilities. We will come to that later on, right. Okay, right now just assume that I can describe it this way, right, whatever the distribution is. Let us see. Okay, we leave it at that for now, right. Okay, so now we come to your question about what is conditional about this, right. So I will write this, then I will explain that. Okay. So a stochastic process So we have a stochastic process xt like before. It is defined as a Markov process, right. So again this Markov is memoryless. So we looked at the geometric being memoryless and exponential being memoryless. So that in general memoryless property is called a Markovian property, right. So this process is called a Markov process if it has this so called memoryless property. It is not completely memoryless, but okay. So I have a set of t values, right, of n time instance, okay. Then the conditional probability, the conditional distribution of x of t, okay. Given the values of So given that at time t naught x took this value, at time t1 x took some value and so on. So even though I have this past history of, I have looked at the n plus 1 time instance t naught, t1, t2 and so on up to tn, I am now looking at the system state at time t. The system state at time t only depends upon the system state at time n, right, tn, then that is considered as a Markov process. Okay. So that is right now a definition, and later on we will see how this actually can lead into exponential time for Markov, the holding times are exponential and so on. Depends only on x of tn. Okay. In other words, the probability, if you want to formally state this, so t is the current instant that I am looking at, right. So what is the distribution for x of t given that I am sorry for, yeah, so this is, so this is the formal property for a stochastic process to be called a Markov process, and mostly we look at this requirement. Okay. So this is need not be the true all the time, right. So let us say that you are asked to measure, right, the so called mess quotient, right, your satisfaction with the mess, right, on a daily basis, right. Every day you are asked to, you are given a scale of 0 through 10 and 10 is very high and 0 is very low, and each day you are told, right. So each day let us look at x of t as on a daily basis, and x is basically your report of satisfaction with the mess, right. Now in a real system what will happen, right, on a daily basis, depending upon if you if I ask you today, right, the food might be good today, but you might have also think that, right, look at the last few days of history, there is some short term memory that we always have, right, that the food was bad over 3-4 days ago, therefore that will always modulate the way that you express your mess quotient, right. So in that case you are trying to hold on to history, whereas if you completely, well, this is still, there is some memory only depending on the current state of the system will dictate the future state of the system, right. So if I were to have a system where your mess quotient simply depends upon what you quotient was yesterday and then whatever you are having today, right, there is some distribution based on what you are having today, then the rest of the events, right, rest of the state of the system is completely is not needed, right. So what it means is that your current system state has captured is a summary of all the past states of the system, right, that is this particular property. If it has, then we can prove some nice properties and use this to essentially try to solve some of this and get some equations and things like that. Okay. So that is, this is one simplification, but this is if you have this, then it is easy to do some of the, otherwise then you do not deal with this fairly complex distribution that P of the combined nth order distribution gets simplified when you look at something like this. Okay, so this is essentially what we mean by a Markov process. A Markov process is by definition memoryless. This future state of the system depends only on the current state of the system, that is it. All the other past history is simply subsumed in the current state. So that is what we mean, right. So regardless of this is what is the distribution of x of t, where t is, right, greater than tn, even though all these were the previous states, it simply depends upon the fact that what is given that the last state was x1, that only dictates my future state of the system.